Then I can restart it. So, yes, so to do the introduction again, so now we do reconstruction of CVC5 proof in a different interactive proof assistant. So instead of having lambda pi, which Melanie did from Leo in lambda pi, now we have CVC5 in Isabelle Hall. So we change every system, but it's the same idea. So the floor is yours.
Thank you, Matthias. Yes, so I want to talk about the reconstruction of CVC5 proofs in Isabelle. And quite a few of my co-authors of this project are here, so Matthias. Of course, then Bruno just told us about Kakra. Hans-Jörg will talk after me, I believe. And then we also have Jabiana Jakpo and Clark Barrett from Stanford, Andrew Reynolds and Cesare Tonelli from Iowa. And I think that's it. So let me start with the actual content. I will keep this brief because you've heard this earlier today, but basically when I use an interactive theorem prover, I want to focus on the big creative argument behind my proof. I don't want to be stuck proving some helper lemma that is important for my proof, but usually on pen and paper, I would never bother with it. And interactive theorem provers are great for that because they offer a lot of expressiveness. So there's already a huge library of everything I might want to talk about, from quantum computing to some theoretical math results, and so on. And also, and we've heard that before in Bruno's talk, they offer a high level of assurance. I always give this example because I really like this verified microkernel, cell 4, that is verified in Isabelle. Okay, as I said before, then in practice, your experience might be different. You might have your idea of how the proof is supposed to work, and then you spend 80% of the time on some lemma that you did not even know was part of the proof, and that seems not very important, and where you feel like the machine should be able to do that for you. And Isabelle already has pretty good automation in that respect, so you can use Sledgehammer, and this tool will then call external provers that might be faster, but maybe less trustworthy. And then it can use the answer of these solvers, for example, which facts they learned, to find an internal proof with its own proof methods inside of Isabelle. And this is what happened here. So, for example, Vampire suggested that it could solve the problem using some facts, and then Isabelle found an own internal method to replay that proof. So this is all well and good, but this does not always work. So even if Isabelle learns which facts the solver uses, what can happen is that it can still not find the proof on its own. And one thing we can do is to have the solver return more information than just this unsat core. For example, we could ask it to explain how it actually reached its unsatisfiable result. So we want to show that a lemma is valid, so we give a negated version to the solver, and then the solver has to show unsatisfiability. And if Isabelle can then look at the proof and go through each step, this is far easier than to find the whole proof on its own. So this is an overview how this would look like. You have Isabelle on the top and you have your lemma. This is then encoded into an SMT-lib problem and given to an SMT solver, which then produces a proof certificate that is given back to Isabelle. That, of course, has to be passed in, but one important step here is the reconstructor. So it has to go through the steps in the proof and then make sure that it can replay whatever the solver, the SMT solver, has done. And then hopefully you end up with a proof for the original lemma. Currently, Z3 and Verity are supported this way. and have been doing good work to help people prove their lemmas easier and more automatic. We wanted to actually add more solvers this way because the more the better. Different solvers have different strengths. And while we did that, we encountered some issues which made us believe that there should be an easier way to add a new proof-producing solver to Isabelle in this way where the proof is actually replayed. So while that being our goal, I will also always talk a little bit about the case study we did where we integrated CVC5 into Isabelle. And this will come up after I explain each step. So first we have to talk a little bit about the solver side. So what do we expect our solver to output? And we will then see an evaluation on specifically what we did on CVC5. Then we will talk about the modifications of the Isabelle side. And finally, and let's see how much time we have, I want to introduce some of the tools we came up with to make this process easier. Also for future solvers, or maybe if you want to update a solver version, we came up with some handy subtools and plugins that you can use to make this whole process less painful. Okay. So adding a new solver can be done in different ways. What you can do is to just support whatever proof format your solver outputs. However, this is quite tedious and takes a long time. We do have evidence of that by looking at the Verity and Z3 reconstruction, and it's not something you might want to do just to support your new solver. But since we already have the formats that Verity and Z3 output supported in Isabelle, the idea would be if you just output in one of these formats, that then you don't actually have to do anything on top of that, and the reconstruction should just work. The Z3 format is quite coarse, and it's not as well documented as might be good for this reconstruction. I think even the authors of the integration of Z3 into Isabelle were a little dissatisfied with that, and there are also some bugs. And then Verity, as we've just heard in the last talk, has an output format that is now called a let, and that is generic enough for our purposes and has, even though a paper specification, although there's some things in the works there, it does has a detailed specification. So our approach was to work with the second format called a let. Okay, so in this case now you would still generate the SMT-lib problem, give it to the solvers, but then several solvers would use the same reconstruction code. So an alert proof certificate can be given and it should not depend on which solver has produced it. So what do we do now if the solver that we choose, for example, CVC5, does not natively generate alert proofs? Of course, we could make it, but another approach would be to have it translate the proof from one format to the other. We also just learned in Bruno's talk something about how Karkarak will be able to do translation. In this case, we chose not to do it externally, but internally in the SMT solver. So CVC5 has a backend, and if you give it an option, it will produce alert proofs. And the way it does that is that it first produces an internal proof, and then it translates that into an alert proof. The internal proofs in CVC5 are CPC proofs, and CPC is this calculus that has some rules, such as the one on the left-hand side there. This not implies elim1, where from not f1 implies f2, we can infer f1. And each of these proof rules now needs to be translated into an alert rule. In this case, it's super easy because there is a very similar alert rule that asserts the exact same thing, and we can just directly map it. In some other cases, it's not as simple. Bruno has already talked a little about resolution, for example. And of course, translation always adds some overhead, and we have evaluated on the example of CVC5 how that overhead manifests. And I want to show you the results of this evaluation, but first let's quickly talk about some cases where we don't want to do a manual translation because there are just so many rules, and that is term rewriting. So CVC5 has a lot of term rewriting rules. And while we could translate them all, so in CVC5 have some code that says, okay, translate this rule into this other let rule, this would take longer than my PhD. So we don't want to do that. Instead, we have written a paper about this also. We have this tool Isarare that can take a rule in this. It's basically like SMT-lib syntax with a little bit of added syntax, and then it can parse it automatically into an Isabelle lemma. And we now extended Isabelle so that it can actually use these lemmas for reconstruction. So if you have a CVC5 proof certificate with some step in it, that is an instance of some rule, then this lemma can be used to discharge that proof obligation. Okay, but now finally the evaluation that I promised. For the evaluation, we first used SMT-lib benchmarks, and then we realized how very different they are from Isabelle generated problems. I think everyone realized, but I had a big aha moment. So we actually decided to use problems that do come from real Isabelle goals. And thankfully, there's the 17 provers paper, a big comparison, and they have generated some really nice benchmark sets. And basically it's one benchmark set, but they add a different number of facts. So if you call Sledgehammer, it will automatically select some facts it thinks you will need to prove your goal. These might be other lemmas or some definitions. And if you then generate an SMT problem, you could, of course, include a lot of these other facts or only a few. And what the authors of this paper did is generate the same goals, but with more or less facts in them. And what we want to do is we want to compare the internal CPC format with the ALET format produced by CVC5, and then we also want to compare against Verity's ALET proofs. Okay. First, the number of solved instances. So the teal color here is the CPC proof, and the red color is the ALET proof. And the first we can see is that for Sledgehammer, this is a really, really generous time limit, but actually decreasing the time limit didn't make that much difference in these results. We see that there are not that much fewer benchmarks that we could not solve when we used the translation. In Verity, we could actually solve fewer benchmarks, which is not a surprise. So Verity was, I think, programmed to showcase that you can generate proofs super efficiently, and is actually pretty competitive here. But the greenish bar is the result that Verity gives. So how many of the benchmarks can the solver produce a proof for in the time limit? Okay, so now I have one good and one bad graph. From my perspective, I guess. The left graph here is the good one. And this one, same colors again, shows that we're actually far faster in producing these proofs than Verity is. So both the CPC and the ELET proof, CPC5 ELET proof, and we actually have very little overhead in translating the proof. That was pretty good. This, I must say, does vary across benchmark sets though. Not on these benchmark set, but if you, for example, would check SMT-lib benchmarks. And then on the right-hand side, we have the proof size, and that's the bad news. And this is actually pretty bad news. So what happens here is that the CPC proof is always smaller than the Verity ELET proof. And smaller here, we count the number of steps. But the CVC5 ELET proof, so the proof after the translation, is actually bigger than the Verity proof, except in one case. And this is actually not great because one of the bottlenecks that we do have on the Isabelle side right now is parsing, and if the proof is larger, this is going to lead to more performance problems. But there is something we can do there when we want to optimize Isabelle for CVC5 proofs. Was there a question?
No question.
Okay. I can't see the auditorium. I can only see the speaker / the non-existing speaker. So please do let me know if there are questions. Okay, yeah, because this is the end of my talk.
Oh, okay. Then I have
Plug
questions.
this in into Isabelle. Thanks
No,
for
I
your
have two
attention.
questions.
No, maybe I should actually try this out first. This is maybe a little quick for me to say we are done. Okay, so we did plug this in into Isabelle. And we actually did not have the experience that everything worked and we were done and I would be able to end this talk at this point. So there were some roadblocks there. One was that Isabelle actually did not support the whole standard, partly also because Verity was still under development when the Isabelle reconstruction was developed. And that also the standard was written at that time. So that is the first point, but also if you only give Verity certain problems in a certain form, it will produce certain proofs on them. Whereas CVC5 might produce proofs that do different things. For example, CVC5 and bit vector proofs sometimes generate XORs, even though there are no XORs in the original problem. Verity actually does not support the theory of bit vectors, and also for anything else does not generate any XORs. So this operator was never translated from Isabelle and was also never parsed. There was never any parsing support for it. Then sometimes proofs outside of the standard were supported. And it was not super clear when this was the case and what proofs were exactly supported. And even updating to a newer version of Verity, where some bugs were fixed, was not always possible or not always easily possible. When we looked into why this was the case, one insight that we had were that some parts of the Isabelle code were too coupled. So, for example, encoding and reconstruction were very coupled. When the original reconstruction was done to test a specific proof rule, so for example, we've seen the implies elim proof rule. If you wanted to test that, you would have to write a lemma in Isabelle and then hope that the corresponding proof would actually contain that rule. And this led to some examples, for example, for the 1-point rule, where there was only ever one regression to test it. And that, of course, leads then to assumptions how this proof looks like. And then maybe if you get other 1-point rules, this is not going to work anymore. And Also, if you want to make a change to a reconstruction method, you still have to go through the whole translation process. Then the alert specification was sometimes unclear, and there were also some minor parts that were wrong. As Bruno said, this has been also uncovered with the Kakara development, same as here. And then there were some new rules that were not supported yet. And we refactored the Isabelle code, but we also worked on the alert standard, which then in part made us having to change Verity, which I'm so grateful for this team and what everyone has done. This was a huge effort because if you change the standard, you have to change all the backends, including Kakara, including Isabelle. You have to change both of the solvers that output it, CVC5 and Verity, and to be able to reach this the status we have where everything actually works with each other is not something that just comes naturally. So this is a really great achievement, and I think we're in a good state right now. I wanted to show you a demonstration if this will hopefully work. So this is a small lemma with words in it. So this just says that if you have a bit vector, so a word that is of bit width 3 and that is greater than 6, then it has to be 7. So it's kind of a pigeonhole lemma for bit vectors, if that makes sense. It seems easy, but it actually, the proof has a few nice rules in it. So what happens is that first the encoder generates this SMTLib problem that we can see down here. So the 3 word is now encoded into this bitvec3 in the SMTLib problem, and then we have the goal being this assertion here. And then we invoke CVC5 on it and parse back in the result, which is this proof here in the alert format, and then we go through each step. For example, there's one of these pesky reordering steps Bruno mentioned, and one step that is really here, a bit vector step, for example, is this bit blasting of a variable, and all of these can be successfully replayed inside of Isabelle. And of course, bit width 3 is pretty small, so before I get that question, how big can we get? I actually prepared a lemma with 32, 64, and 128. And in all of these cases, we can reconstruct the whole proof, even though it ends up having quite a few steps. Okay. So let me
Hanna,
yeah.
you should come to an end.
Sounds good. That was what I was just going to say. So one thing I do want to talk about it before we stop is the second part. So we've talked about the Isabelle modifications, but what about the evaluation? So how do we evaluate this? And one problem was that we couldn't have a direct comparison because solvers would use different formats. But now we actually have two solvers with the same format, which means we can compare them far more easily. And for that, we built a testing infrastructure so that Isabelle can actually parse external SMTLib proofs, problems, and then check them against a proof that you give it. So we kind of circumvented the translation, which helps with the decoupling of these both sides. I show you the result here. So this is our check SMT tool, and as you can see, it is dealing with a lot of steps here, but it is taking this test problem 2.smt and it's taking the let file, and then it goes through every step here and checks it. Okay, let me fast forward to our results. You won't have much time looking at them now, but I heard there's a YouTube recording, and also we will have a paper at ITP this year. So basically, we had some good success reconstructing these. However, I do want to mention that our timeouts are still higher than they would be when used with Sledgehammer. And we still, and I talked about the proof size, do have some further work to do to make this work more performant. That said, the whole proof reconstruction on the Isabelle side was fine-tuned for Verity. There was a separate paper for that, actually. So we will have to maybe do something similar for CVC5, where we speed up the checking of some rules that occur off. Okay, to summarize, we have tested out this translation approach and have shown that it's pretty feasible. There's very little overhead in terms of time. We did a lot of work to contribute to the ELAT standard with this. We also refactored the SMT tactic implementation in Isabelle and supported CVC5 as a new solver. Currently, we're working on supporting more bit vector proofs. And we have some testing tools that I did not all show you, but the most important part is this check SMT, where you can check external proofs. Okay, if we have time for it, I'm not super sure. Feel free to ask some questions.
Thank you very much.
I have one first question about ISA rare. So like you say that you are able to take like all the rules of rare and then like convert them in Isabelle, but are you also looking for the, like you generate the proof also, or like you have to manually take all of them and then like prove them?
Good question. So for a lot of them, we actually produce automatic proofs. That said, a lot of them are also quite easy, so you can like try auto and that works often. We do have a little bit of a more elaborate. Okay, so our goal is to actually translate this this rule into a goal that only uses already existing Isabelle operators. So one extension these rules have compared to SMTlib is that they can use these lists. And actually what we do is we generate kind of a proof skeleton that gets rid of these this extra data type we made to encode the lists in Isabelle. So
Okay,
that
I
the
see.
user gets a lemma only in terms of fold, which, you know, the user will know. But they don't have to like learn about our Isabelle fold. And then it does, for some of the data types, apply some induction. So for these lists, we usually want to prove them by induction. So it automatically adds also these proof stubs for that. But if it's more complicated than that, you do have to prove it yourself. Yeah. And we have proven most of the rules, except for bit vectors. There's a small percentage of rules that we have not proven yet.
Second, you mentioned that you have a problem with your parsing. Like how it can be like, it's hard for me to understand why parsing can be a problem. Maybe it's because of Isabelle implementation. I don't know.
Yeah, just an implementation. I think we could revamp that at some point.
Okay.
So I think there is something we could do there to make it a little more speedy. I could assume because the original proofs were maybe not that big, that parsing was not that much of a bottleneck. And as I said, our proofs are significantly bigger, so this becomes more of an issue. So maybe that would be a good next step to work on that.
Because I saw like, in your benchmark, like you found a proof of bit vector that's like quite small, and in the SMTlib benchmark, like I didn't find any proof that is like smaller than 100,000 of steps. So like that, yeah, it's quite challenging to construct this vector.
Yeah. We do have quite big proofs though we can reconstruct.
Okay.
I would like to, as a next step, make a similar benchmark set to the set I showed you, but with bit vectors. But for that, I also needed to do some smaller things in the translation of Isabelle word lemmas to SMTlib, and then run these things on the benchmarks that have SMT-lib bit vectors in them and see what structure the proofs have. Yeah, that would be interesting.
So we don't have time for more questions, but I have good news for you. You will both be at ITP, so you can be able to discuss there.
Yeah, we'll
So
see
if
each
you have
other
more
next
questions, remember them.
Okay, sure,
And
sure.
Matthias knows more about this than I do. So you can hit him up during the happy hour and
we'll see
ask
each other
him
at
questions.
ITP. I'm going also.
Nice.
So thank you
Okay.
very much, Hanna. And let me this time not forget to stop the recording.